Hello and welcome to the week 12 lecture on alchemy and the chemical revolution. I want to start by first showing you the outline. And as you can see, it's kind of a detailed outline this week where we are going to be looking at alchemy and chemistry, starting with the historiography of alchemy and chemistry, then looking at what Principe in Secrets of Alchemy refers to as the golden age of alchemy, looking at chrysopoeia, which is, if you remember, the making of gold or the idea of transmutation of metals in order to make gold, and efforts to make the philosopher's stone in order to be able to have that kind of catalyst to be able to turn base metals into the noble metals. If you remember this, it's a little bit of a review. But he talks in his chapters then about, how do you actually do alchemy? How do you make a philosopher's stone? And so we'll talk a little bit about that, and then turn to the other major aim of the golden age of alchemy or of early modern alchemy, which is the making of medicines. And again, we saw this for the medieval period as well. So we'll do just a tiny bit of review to remind you of what we talked about, kind of get you up to speed, and then look at the early modern developments along these lines, and then look at the decline of alchemy. And in particular, this is sort of my interpretation of this period, because what Principe argues is there's really not a difference between alchemy and chemistry through the ancient, medieval, and early modern period, and you only really see a development of what we think of as modern chemistry, moving into the very late 18th century and then into the 19th century, which is usually considered to be part of the modern period. What I found when I was trying to think through this lecture and put it together and conceptualize these developments, I actually found it more useful, and it actually seemed to me a bit more accurate to separate the two out as we move into the 17th and 18th centuries, and basically the time of the scientific revolution, because it seems to me that what made up alchemy from the ancient through the medieval and then the beginning of the early modern period, it really starts to change when the mechanical philosophy starts to get involved. So both alchemy and chemistry deal with what is matter, what is stuff made of, how does that stuff behave, how does it get the qualities that it exhibits, how can you explain changes in the material makeup of terrestrial substances? This is all part of what alchemists and chemists study. So it's kind of the same goals. It's got the same questions and a lot of the same procedures, but what we're going to see is that those procedures become much more experimental as we move into the scientific revolution and that period, and especially once the mechanical philosophy kind of gets involved. And there's a major change in terms of how those experimentalists are thinking about matter and what they come to find out. So what I noticed was that once the mechanical philosophy gets involved, what people are doing and talking about and thinking about resembles modern chemistry much more closely than before the mechanical philosophy. So what I decided to do was have a sort of an alchemy part of the lecture that sort of comes up to the point of the mechanical philosophy, and then look at what happens once the mechanical philosophy starts to include sort of alchemical ideas or chemical ideas, starts to include the investigation of matter theory and how matter behaves. Once that happens and it sort of comes into the purview of the mechanical philosophy, then I'm going to start to call it chemistry, or at least early chemistry. And so that's sort of what we're going to be looking at. Again, sort of looking at the historiography, then this quote-unquote golden age of alchemy, as Principe argues. Within that, looking at the making of gold, so the chrysopoeia that we've talked about before, chemical medicines, how these things develop in the early modern period, and then the decline of alchemy. So around the turn of the 18th century, alchemy, and particularly transmutational alchemy, really starts to go into decline. And honestly, nobody really knows why. Nobody's been able to really explain it. I'm going to try. I've got some ideas here. I've actually done a fair amount of research on chemical medicines and how they affected the history of pharmacy. And so from some of my own research, I've got some ideas. And then, reading Principe and other works on the history of alchemy, I'm going to sort of bring that together and then give you a few reasons as to why we think it's declined. But this is an area of history that definitely needs further research. We really don't understand that decline very well. Then we're going to turn to the mechanical philosophy and look at, sort of review ideas of mechanism and mechanical philosophy and then look at how it relates to matter theory. And then we're going to look at a series of steps then that lead to what historians of science have called a chemical revolution that is part of the overall scientific revolution, but it's considered to be sort of a late a latecomer in the scientific revolution, whereas most of this mechanical philosophy and the Copernican revolution, as we've seen, sort of begins in the mid 16th century and then concludes by the end of the 17th century. The so-called chemical revolution doesn't actually conclude until the end of the 18th century. It takes sort of another 100 years for chemistry to kind of come together as a scientific discipline that has something that resembles its modern ideas and practice. And so we're going to look at 3 steps that kind of lead to that. First, the recognition of vaporization, which means the recognition that basically all matter can be vaporized if it's just heated to a high enough temperature. Then along with that, there's a series of discoveries among different natural philosophers, or we can start to think of them as scientists and possibly chemists who realize that there isn't just one kind of air, as Aristotle had thought, and as everyone who'd investigated these ideas for millennia had thought. Instead, what they start to realize is there's a whole bunch of different kinds of airs that are mixed together in atmospheric air. And then that leads to investigations of combustion, or basically when things get burned, get heated up and burned, what happens in that chemical reaction, and the realization that its oxygen is actually being fixed into materials when they are burned. And then the isolation of oxygen, the isolation of other gases, and very importantly hydrogen, sort of come out of these experiments. And then with that, the realization that hydrogen and oxygen together make water. And so what you've got is 2 of the Aristotelian elements of air and water have now been shown to be very, very different than Aristotle had conceived of them, and that others had conceived of them ever since, as elements. Now we're realizing no, air is actually a whole mix of different kinds of gases, all earthly matter. So even earth, Aristotle's element of earth can be vaporized, it can be liquefied, and it can be vaporized, again, if it's heated up to a hot enough temperature. And that water, again, is composed of a mixture. It's a compound of hydrogen and water. And so here we have the chemical equivalent of the destruction of the Aristotelian universe that we saw with the Copernican revolution. So now matter theory is sort of being taken apart. And when you combine that with the growing conceptions of atomism, then you come up with the something resembling the modern ideas about the atom. It's definitely changed since the later 18th century and the early 19th century, but you get once and for all a sense that elements are actually composed of atoms. There's a whole bunch of different kinds. There isn't an infinite number, but there's a whole lot more than just four, and they act by combining with one another and then separating from one another based on actually ideas of affinities, which actually brings in Newton's ideas of these affinities from gravity. And if you remember, we talked about this last week about how he wanted to get rid of that Aristotelian notion of sort of these innate sort of active principles. He could not, and actually that whole idea, which he writes about in the Principia as well, he actually writes about how there must be then affinities, attractions and repulsions of matter, as well beyond just the concept of gravity. So that's a long introduction to what we're talking about today, but it gives you kind of an overview. And so the ideas are going to be chrysopoeia, so that transmutation of metals to create gold. Paracelsus, who was a major figure for chemical medicine. Robert Boyle, who does a lot of work with the differentiating different kinds of airs. Phlogiston, which I'll get into later. It's sort of a complicated concept to talk about here, but it's sort of anti-oxygen, the sort of the opposite of oxygen. And then Antoine Lavoisier, who is the Frenchman who is credited with sort of realizing what happens in combustion reactions, and through that is able to identify oxygen, and then from there hydrogen as well. And put a whole new language on chemistry, which is largely the language that we use to this day. And I just want to say too that in the readings, there's the nomenclature, the chemical terminology that's used prior to Lavoisier can be really confusing because there was a whole different way of naming things that had very long traditions. And so you'll see, words like vitriol and saltpeter to name compounds that today we have sort of chemical names for. And so it can get really confusing. And what I would say is, don't worry too much about, keeping track of all these different chemical reactions that they're talking about in the readings, but rather keep that overall picture in mind of what it is that through these experiments that these chemists are trying to do. So, and hopefully the lecture will clarify some of that for you as well. So let's move then relatively quickly through the historiography. I just wanted to point out, there's a couple of points here I wanted to discuss about the historiography. The first, that I've already talked about a little bit, is the fact that this chemical revolution we're talking about, for which Lavoisier is the one who gets the main credit for it, is considered to be sort of a latecomer to the scientific revolution. Like I said, it's really sort of a century later, whereas most of the scientific revolution is considered to be encompassed in the 16th and 17th century. We saw Barrera talk about the early scientific revolution in the Spanish Empire. Then we looked at the Copernican revolution, and then the move to the mechanical philosophy, atomism, and then the sort of Newtonian laws of motion and laws of gravity, which is sometimes referred to as a Newtonian kind of revolution in physics. Now we're looking at the chemical revolution, which is a bit more complicated because it's hard to identify sort of modern chemistry in earlier alchemical pursuits, and because the sort of quote unquote chemical revolution concludes sort of a century later. People are definitely doing work on applying atomistic theories to air, differentiating different kinds of airs in the 17th century, but it takes really another century before people begin to realize what those airs are, how they behave, and then from there on to a new theory of the elements that really gets rid of Aristotelian theory once and for all. So it's considered a late chemical revolution, and then there's also the whole issue of the differentiation between alchemy and chemistry, and the role that they play in the scientific revolution. When we're getting into the late 18th century, can we still talk about these experiments that, say, Lavoisier is doing on, matter and on gases as alchemy, or are we now talking about chemistry? And what Principe argues is that you really can't differentiate the two. They're really one and the same. The only reason alchemy is called alchemy is because of the when it went through its development in the medieval Islamic period. Islamic alchemists just added the al, which is basically the definite article, the word the. It just basically means the chemistry. And so chemistry and alchemy etymologically, which means the history of these words, their meanings are basically exactly the same. And the way he kind of gets around this, differentiation or lack thereof of alchemy and chemistry is by referring to it as chemistry, to sort of indicate that in the early modern period, alchemy and chemistry were basically one and the same, but they were a bit different from our modern ideas of chemistry. I have to say that I have not found that very satisfactory. I just keep seeing the word chemistry and I can't, it's hard for me to sort of understand what is meant by that. And I actually prefer the differentiation between alchemy and chemistry. To me, alchemy is just early chemistry. It's chemistry before, the chemical revolution. That's the way I sort of think of it and understand it. And that's how I would recommend that you do too in this lecture. And that's how I'm going to treat it. It may be a bit anachronistic of me, but I just find I've read a lot of Principe's work and that of another alchemical historian, William Newman, who I'll talk about in just a second. And I really like their work, but I just can't rally around the chemistry term. I just find it actually becomes distracting. So anyway, that's one of the things I want to say. The other is that in the history of science, and the traditional interpretation of alchemy that Principe talks about this, is that alchemy was, and you'll often see this in sort of modern ideas as well. This is sort of our general, everyday understandings of alchemy, or its kind of reputation is that of a field of superstition. It's superstitious, it's magical, whereas then chemistry is scientific and rational. And what I really like about Principe's work is he tries to really break this down and certainly show the spiritual aspects of alchemy, and he talks about all the religious symbolism that goes along with it as well. There's a lot of kind of symbolic meaning that's attached to alchemy, but that doesn't mean that it was irrational. It doesn't mean that it was backward or some kind of pseudoscience, before the chemical revolution. That's how it's portrayed in the traditional interpretation of the scientific revolution. Alchemy is magical, it's bad, it's, only when chemistry gets rid of alchemy can it ever progress and become modern. And I think what Principe does a wonderful job of arguing, and what I fully endorse and embrace, is that alchemy taught its practitioners about matter, about the behavior of matter. It led to the development of all kinds of alchemical and later chemical apparatus and procedures and operations. And I mean, if any of you have taken a chemistry class, you know that distillation is an absolutely central part of chemistry to this day. It's developed through alchemy. So without alchemy, we wouldn't have chemistry. It set up the basis for what practitioners could later do and learn about matter. So it's incredibly important to the development of chemistry. And so along with that traditional interpretation that really sort of puts down alchemy is that same idea of the march of progress, that you only see the field of chemistry progress when it gets rid of alchemy, when it's no longer affiliated with the superstition and magic of alchemy. And we are certainly going to be arguing against that here as well, and looking into the revisionist interpretations. So, as you can probably imagine, Principe, so the author of the book Secrets of Alchemy, is one of the people who has written a lot about alchemy and takes a revisionist approach to the history of alchemy, takes it very seriously, sees it as providing a really important basis for the chemical revolution and the development of modern chemistry, and sees it as, a really viable, important field of early science, if you will, or of natural philosophy. And what he and others have argued is that alchemy and chemistry, as I talked about a few minutes ago, are really intertwined. These are intertwined histories, and instead of trying to use the term, is it alchemy, is it chemistry, instead they use the term chemistry, and I've already talked about how it just has never really, I've just found that term distracting and kind of unsatisfactory, but it's their way of really trying to get away from these traditional interpretations. And as I've already talked about, and as you can imagine, they emphasize the contributions of alchemy to the scientific revolution and to the chemical revolution, and they take it really seriously. They don't just sort of call it a pseudoscience or it's sort of magical. They certainly take into account all the kind of symbolic and religious meanings and even sort of spiritual, metaphysical meanings of alchemy, but they take it as a serious kind of scientific practice in the pre-modern world. So again, they emphasize the contributions of alchemy to the scientific revolution. And I just wanted to show you then a few books and authors who have really kind of revived this revisionist approach, or I should say established this revisionist approach to alchemy in the last kind of 20, 30 years or so. Prior to their work, really, in the traditional accounts of the scientific revolution, alchemy was just disparaged, dismissed. If it was brought up, it was brought up as this sort of ridiculous pseudoscience. And so Principe and then another historian, William Newman, have both worked very hard to, again, bring alchemy into the narrative, the historiography of the scientific revolution, and have really worked hard to get other historians to take alchemy, the history of alchemy, seriously. For instance, starting in 1994, Newman, who is a professor at Indiana University, published a book on George Starkey, who was actually an American um, academic, I guess, a scholar who did a lot of work in alchemy, and he wrote these voluminous notebooks, laboratory notebooks, where he was making different kinds of medicines. He was trying different kinds of transmutation, making perfumes, essential oils, and things like that. He left behind a bunch of notebooks, and so both Newman and Principe have done some serious work on George Starkey. I should say he lived in the 17th century and then actually ended up moving to England and then working with Robert Boyle in London as well. We'll talk about Boyle more later on in the lecture. Then in 2005, Newman wrote a book called Promethean Ambitions, where he sort of furthered his arguments about the importance of alchemy. Then Newman and Principe together published George Starkey's laboratory notebooks in 2005. You can see here, that's the middle book there. Then in 2006, Newman published a book called Atoms and Alchemy, where he argued that what you can see atomistic theories and ideas in alchemical works as early as the Middle Ages. And then in 2010, wrote another book called Alchemy Tried in the Fire. So you can sort of see the sweep of his and Principe's work here. And I should also say that Newman translated the Pseudo Geber, his book on the Sum of Perfection that we talked about from the Middle Ages as well. And he argued that there was an early atomistic theory in that. And then also in the historiography, there's been a growing realization among scholars that some of the sort of heroes of science, Robert Boyle, who we'll talk about later in the lecture, had discovered what's known as Boyle's law of the relationship between volume and pressure, and then also Newton, who we've talked about at length in this class, that both of them practice alchemy a lot, did a lot of alchemy actually. That first came out in 1983 by in a book called The Foundations of Newton's Alchemy by a historian, Betty Jo Teeter Dobbs. And then in 2000, Principe wrote a book about Boyle and his alchemy. You can also see that in 2003, an alchemy reader of primary sources came out that goes from the ancient times to Newton and will include some of Newton's writings as well. And then just when I was putting together this lecture, I just found out that Newman has now written a book called Newton the Alchemist that is coming out in 2019. So you can see just how important these two historians, Principe and Newman, have been in the history of alchemy, and the ways that they've brought out a lot of important themes and works, and showing just how important it was in the early modern period, in the time of the scientific revolution, and that a lot of really important natural philosophers were pursuing alchemy, and not just here and there, but actually had spent a lot of their time doing this. So here's an image actually of one of the laboratory notebooks of Robert Boyle, of his alchemical experiments actually, that is now housed in the Royal Society. And then here are some images of Newton's alchemical notes. These actually came up for, I don't want to go too much into this, it's a really interesting story. They came up for auction early in the 20th century, and everybody was so horrified and embarrassed to realize that Newton had actually practiced alchemy that these papers were auctioned off at very, very low prices and sort of spread out all around England and actually all around the world. And then scholars have been trying to get them back together to now be able to pursue, to be able to understand what it was that Newton was doing in his alchemical experiments. And this goes along with that historiography that's taking alchemy much more seriously now. And then there are a number of historians who have also approached the history of alchemy from the perspective of commerce and business, sort of the business aspects of alchemy. For instance, we've got Pamela Smith. You may remember her from the lecture where I talked about the importance of artisans in science, and that she's a real pioneer of that idea, that facet of the scientific revolution. And she wrote a book called The Business of Alchemy. This is actually her first book. And then we've got her student, actually was Tara Numedal, who wrote Alchemy and Authority in the Holy Roman Empire, and is actually about to come out with a book on a female alchemist. There wasn't an image of it. It's coming out in 2018, otherwise I would have put it here. And then again, here you probably see on the right, you probably recognize that book, right? The Secrets of Alchemy by Principe. And I should say you can't see the dates of these. They got hidden, unfortunately. I think you won't be able to see them. But Pamela Smith's book came out in the late 90s. I think it was 97. Numedal's book came out in 2007. And then Principe's work is, I believe it was 2012. So you can again see these kinds of the sort of the history of the historiography, the history of these differing interpretations. And I should say all of these books then also see alchemy as an important artisanal pursuit as well. So these alchemists are seen as artisans who then are contributing to the scientific revolution as well. So that's where you can see some of the historiography of alchemy. But now I want to turn to the golden age of alchemy that Principe had talked about in his chapter on that on the golden age of alchemy, and in particular what that meant. What does it mean to practice alchemy in the early modern period in the 16th and 17th centuries that he refers to as this golden age? So I want to start but with chrysopoeia and the making of a philosopher's stone, and then we'll turn to some of the developments in chemical medicine as well. So what Principe talks about in that chapter is, what was it that an alchemist did? How would you make the philosopher's stone? How would you go about doing that? And just to do a little bit of review, if you'll remember, I'll talk about the quote in just a second, and the image too. But just as a little bit of review, if you'll remember, since we haven't talked about this in a few weeks, when we began talking about alchemy, um, we we said that we when we began to study it, we looked at its origins in the Hellenistic period, people's works with metals and trying to counterfeit metals as well as trying to counterfeit jewels. It sort of comes out of this craft tradition, but it uses what are now widely recognized as chemical apparatus, chemical operations, distillations, water baths. And the idea behind alchemy as it began to coalesce into a discipline was that you could make gold from base metals, and you might think that just seems crazy because now we understand that each metal is a different element. You couldn't possibly, take lead and turn it into gold. But the reason people thought they could was because Aristotle had taught that metals were made of two different sort of exhalations from the earth. One was mercury and one was sulfur, and they combined to make metals. And the most perfect metals had a perfect balance of mercury and sulfur, but other metals did not. But they were sort of the whole idea was that they kind of cooked deep within the earth, and a fully cooked metal would be perfect gold, and that it just took a really, really, really long time for that gold to get perfect, for the metal to get perfectly cooked into gold, and so the idea was that an alchemist could actually try to figure out how to speed up that process because that was sort of a natural process of this cooking of these base metals, and each metal then was considered to be at a different sort of stage of development, with gold again that was the end product. And the alchemist was supposed to be kind of a catalyst. They would try to figure out how can we make gold fast so that we don't have to wait for it to cook inside the earth. Let's try to make gold. They thought they could do that through various manipulations of the mercury and the sulfur, as we looked at in the past, to try to, maybe separate the sulfur spirit out from the mercurial body, and then think of it as sort of in the Galenic terms of a metal being imbalanced, just like a body that was unbalanced would be a sick body, and there you would then give somebody medicines of the opposite qualities to restore balance. It was the exact same ideas with metals. So you try to figure out what the metallic imbalance was and then restore balance, often by then distilling the metal with something to, say, pull out its spirit, then make changes to its spirit, and then combine it with its body to again have sort of a perfect balance. So that's kind of just a review of what we had talked about before. Then what we saw is once that the medieval alchemists in the Islamic world actually expanded these ideas much further and started using all sorts of different kinds of organic materials as well as metals, and talked about basically healing the metals, or applying medicines to these metals to make them into gold, even though it wasn't, you know, they weren't thinking of applying these to the human body. But when these texts get translated into Latin and reach the Latin West, then the people reading these texts, read about these, we can, apply these metals to these medicines to these metals to make gold. And what historians of alchemy believe is that they took this literally. And so people like Roger Bacon started to say, hey, we can actually, find a medicine like a philosopher's stone that will restore balance to the body and allow people to, live a really long time, live for over 100 years, to prolong their lives, to prolong youth through alchemical means. Then you can make medicines that will bring health to the body. So they start to make alchemical medicines. And so that's sort of the state of things as we move into this golden age of alchemy, when a whole bunch of alchemical texts are written, both for chrysopoeia, to make gold, as well as to make medicines, as we'll see. And this slide here, then, now I can get to this slide, is an illustration of that early idea, Aristotle's idea of the exhalations. You've got the yellow, I believe, is the sulfur, and then the blue is the mercury. But these are basically, this is like a picture of these exhalations that are coming out of the earth to make various metals. And this is from a 17th century alchemical text by Michael Meyer, which has actually a lot of really interesting illustrations in it. But one of his quotes is that just as nature produces metals from sulfur and mercury, so does art. So this is basically a picture and a quote depicting that Aristotelian idea of the exhalations, and that through human art, they can actually improve upon what it is that nature can do, or they can supplement and complement what nature does in the ground in making gold. Now the alchemists can do it through their alchemical art. So that's what that kind of image is about. And then here is then an image of the philosopher's stone. Who knows what it would really look like, but sometimes it was described as sort of a red powder or a white powder or a red stone. So I just wanted to show you a philosopher's stone. But what Principe talks about then again is that a whole bunch of alchemical texts were produced during this period in terms of making the philosopher's stone. And Principe himself has carried out a bunch of the experiments that are described in these books. And in that, he actually made a tree, a sort of quote unquote tree, was able to make crystals in a kind of flask that's called a philosopher's egg. It's a very long tube with a rounded bottom. And he was able to make this from what was known as philosophical mercury and gold. He was actually able to do that in his lab. And so, according to Principe, if you were an alchemist in the early modern period and you wanted to make gold, you would proceed by first deciding if you would want to prepare a particular kind of material in order to transmute gold, or if you wanted to try to prepare a universal philosopher's stone that then would transmute any kind of base metal into gold. And so if you decided to go the particular route, there were lots and lots and lots of different kinds of materials you could choose from. And what he says generally would happen then is that you would take some kind of metal or other kind of material and then mix it with gold, if you could get a hold of gold, if you could afford it, and usually most people couldn't, then you would often use mercury, which was a particularly interesting kind of metal to alchemists because it was liquid. Unlike the other metals, mercury is liquid at room temperature. And then you would mix those together, or you could possibly take the material and mix it with silver, and then in that way try to augment the silver or the gold through the mixture with these particulars, basically. For those people who wanted to try to make a universal philosopher's stone, then you would often usually start again with silver or gold or mercury, and then you would put it into one of these philosopher's eggs and actually seal the top of it, put it into a furnace, and then heat it for a long time, sometimes even weeks or months actually, which could be dangerous because the glass could actually explode in the furnace. But if it didn't explode, at least theoretically, what was supposed to happen is that first the mixture would turn black, then it would turn white, and then it would ultimately turn red or sometimes yellow, actually, was sometimes considered to be a philosopher's stone as well. Um, but it would go through these sort of different colors, which had all sorts of important kind of symbolic meaning and were considered to have certain powers as well. But that's largely what you would do if you were trying to make gold. Um, and what Principe finds is that in doing, in making sort of particulars or universal philosopher's stones, these alchemists actually ended up doing all kinds of kind of chemical manipulations and coming up with various kinds of substances, possibly platinum, different kinds of sulfates, and different kinds of metallic oxides. And from this, they were able to learn a lot about the matter that they were working with. Whether anybody actually ever truly made gold is another question. But certainly a lot of people claimed it, although we're never actually able to prove it truly in any kind of demonstration, which leads to a problem, as we'll see when we talk about the decline of alchemy. Um, what complicated all of this, though, is that in alchemical texts there was a use of a thing called decknamen, which was basically different kinds of symbols or names given for substances that were sort of a code name. They were sort of symbolic, secret names that were used that only what they called adepts, people who were very skillful, knowledgeable uh, alchemists who'd had a lot of practice in the field would know these terms, and that they were sort of circulated secretly among the alchemists, and it makes it very difficult for modern scholars to know what they're talking about when it comes to these materials. And there's all sorts of sort of hidden meanings in these alchemical texts. So sometimes if they'll refer to one material, does that really mean just one material, or does it mean one as in the sense of God and the universe is all one? It's sort of unclear. They'll also use terms like dragons, or the green lion was a term frequently used to designate green vitriol, which is basically copper sulfate. So there were different, animal symbols used to represent different substances, different kinds of descriptions of them, again, that don't actually name the actual substance, and you had to know basically what the code was. So I'll just show you some examples. So a very common thing was that in the alchemical symbols, I'll do the bottom line first, that planets were considered to have certain affinities with particular metals. So the moon was affiliated with silver, Mercury with quicksilver, or you can see how strong that affiliation was, that quicksilver even today is called Mercury. Venus was affiliated with copper, Sun with gold, Mars with iron, Jupiter with tin, and Saturn with lead. So when they would have these recipes for making the philosopher's stone, whether it was universal or particular, they would actually refer to, if there was a metal, they would call it Saturn, or they would call it, the sun. Take the sun and mix it with the moon, that, and then mix it with the green lion, and then heat it. That's the kinds of language that they would use, and they also had various symbols that went along with it, which you can see here. And then you can also see that there were alchemical symbols given to the four elements. So if you look at that top line, fire, air, water, and earth had their own particular symbols in alchemy. And then there's also these three principles that we're going to talk about later in the lecture, actually in just a few minutes. With chemical medicines, there was an important uh, author and maker of chemical medicines called Paracelsus, who said, no, it's not, it's not four elements that make up the world, and it's not just sulfur and mercury that make up metals. Actually, sulfur, salt, and mercury are the three principles that make up all material things on earth. And so This was so these had alchemical symbols as well, and there was really symbols for everything. So here's again the alchemical symbols for the various planets that were then associated with different metals. And then here's more alchemical symbols to go along with different metals, and then you can see even more. These are for various. This is actually in French, but these are for various kinds of salts. Ammoniac, common salt, which is sodium chloride, and then another kind of sort of medicinal salt, and then below that is sulfur, black sulfur, and then the sulfur of the philosophers. So these are all these different kinds of terms used for various materials, and then they each have their own chemical symbol, which was again was another way of having this alchemical code only for the initiated. And then here's even more. So there's just tons of them, and there were different symbols for distillation, sublimation, which is a kind of distillation where the thing that's being distilled vaporizes instantly and then reforms as a solid on the top of, say, the pot that you're doing the distilling in. So sublimation was another kind of alchemical operation. And then there's another operation called calcination, which I'll talk about later in the lecture, which is basically just burning things, to produce an ash. And so all of those kind of, we call them thermochemical operations because they use heat to bring about chemical change. These thermochemical operations, each of them had their own alchemical symbol as well. And then here's another example just from that Meyer book I talked about earlier that represents sort of an emblem representing the Philosopher's Stone that actually is an acrostic, which basically means it takes each letter of the word vitriol and then makes has a word that starts with that letter. And so you can see with vitriol, you see the VITR IOL in each of these sort of little triangles around this star with all these alchemical symbols. There's all kinds of symbolism in this that's actually related to things like um, the Masonic movement, and another group of people that formed sort of secret societies called the Rosicrucians. So this is just another example of alchemical symbolism. And then in another book by Meyer, you can see that more of the symbolism, and then along with each of the alchemical recipes that he presented in this book, he actually included a song as well, that the music is supposed to go along with this too. So you can see these harmonies and these symbols in alchemy, in addition to sort of the experiments and the chemical manipulations that are going on. Here's some more imagery, which he discusses in the last chapter of his book, which I've included as an optional reading, and then you can answer a question on it for extra credit. It's really interesting. Here's the green lion devouring the sun, so we know the sun is gold. We know the green lion is vitriol, and when they react, then the vitriol works to displace the gold in the chemical reaction, so that's why the green lion is devouring the sun. So that's sort of the symbolism that symbolizes these chemical reactions that are taking place. And then Principe also talks about the work of Basil Valentine, which was a pseudonym actually. It wasn't anybody's real name. We don't actually even know who this author is. He wrote an alchemical treatise, and he lived in the 15th century. But it's this book called The 12 Keys, and each of these keys is basically a recipe for creating a philosopher's stone that sort of all work together to create this kind of universal transmuting agent. And then on the right is then an illustration of the first key in Basil Valentine's 12 Keys. And I'm just going to stop here and then play for you a 5-minute video clip from that Principe made with the American Chemical Society, where he describes his work. And I thought it was a really interesting way to kind of bring to life the research that he does. And then you can see how this also relates to the Making and Knowing project of Pamela Smith that she's doing at Columbia University, in terms of, making various kinds of pigments and paints and plasters, that there were recipes for in the alchemical texts. And then Principe is doing this as well. He has his own lab. He's a professor at Johns Hopkins University. So I will play that for you now.
Right now, I'm just thinking about how messy my desk is and what you're seeing. Is the shot okay, actually? Good. This is my lab where I do alchemical experiments, that is, try to reproduce the results and the experiments that were done by alchemists in the 15th, 16th, and 17th centuries. To do this, I have authentic labware. So one of the most common pieces of labware is the retort. What you do is you put your substance to be distilled here, put it in a sand or ash bath, and cork it up, heat it, and whatever is volatile will condense here in this part and run out. I also have one that I keep at home that I use on the kitchen stove to distill after dinner drinks in. Right, so I also have some of the products of alchemy here. I actually find it's easier to label them in symbols in Latin to use the old terms than to try and use modern terms for them. This one supposedly, let's see, it contains the sulfur of antimony from the regulus of antimony, which has been sublimed with sal ammoniac. A lot of what I'm involved in is trying to get a better understanding of what alchemy was and what alchemists actually did. This has always been a problem, however, because the texts that they've left us are very secretive. They're often highly metaphorical, they're written in a kind of code, and they're filled with extravagant imagery, often very beautiful woodcuts, but forbidding in the sense of what does it all mean? So these extravagant Baroque images that clutter alchemical texts from the 16th and 17th centuries often have a hidden chemical meaning. It was a coded way of communicating, both concealing from people who are unworthy of the knowledge, but revealing it to the people who were in the know or were worthy of being in the know. So, for example, if we wanted to make aqua regia, a solvent that's able to dissolve gold, today we could take nitric acid and put ammonium chloride in it and make that solvent. But an alchemist might describe it by saying, let the red dragon devour the white eagle. Or, rather than saying it in words, he could draw an image of an actual dragon devouring an eagle. One of the things that I did some years ago was to look at the papers of Robert Boyle, famous character. We all learned Boyle's law about gases. One of the things that I discovered in his papers was a huge amount of work on trying to make the philosopher's stone and transmute base metals into gold. Most alchemists described it as a heavy, red substance, a powdery or waxy substance. And if you were able to make it in the laboratory, you could take just a small amount of it, drop it into a crucible of molten tin or molten lead, and in a few minutes, it would transmute it all into pure gold. One of the things that impressed them the most was the so-called star of antimony. It's a crystalline pattern that develops on the surface of antimony when it cools under just the right conditions. So what they would do is they would take some of the antimony ore called stibnite, put it in a crucible, melt it down, it melts very easily, and add iron as a reducing agent. And if they did it right, just right, sometimes when they took the button of metallic antimony out from underneath, it would have this beautiful pattern on the surface that looked to them like a star. And so if the Star of Bethlehem signified the birth of someone so important, the star here could signify the production of a substance very important to what they were trying to do. As a historian of science, what I'm trying to do is get a truer, more accurate depiction of the past. In particular, how scientific ideas developed, where they came from, who developed them and why. It tells us more about how our ancestors were involved in the same kind of process as we are, about trying to understand the world that we live in, trying to manipulate it, trying to use it for valuable ends. I'm Larry Principe. I'm professor of chemistry and professor of history of science and technology at Johns Hopkins University.
So I thought that was sort of useful to see what it is that he does in his lab and to be able to hear from the author of one of our texts. But now I want to turn to chemical medicine, which is basically the use of alchemy to make medicines for people that we also had talked about from the Middle Ages, Roger Bacon, John of Rupasissa, the pseudo Lul that we had talked about, several weeks ago, where they were um, distilling materials in order to distill out what they saw as a quintessence or sort of a divine ether, and that would make a really powerful and potent medicine that was basically like a medical philosopher's stone that would allow you to prolong your life and to prolong youth, to be able to avoid illness. And they really thought that the use of distillation was this sort of miraculous um, operation that had tremendous healing power, and we saw that especially in the distillation of wine to make basically distilled alcohol. And then there's a huge proliferation of distilling all kinds of different things to make all kinds of different distilled alcohols, gin, brandy, whiskey. And this continues into the early modern period, particularly with the work of a man named Paracelsus, who I'll talk about in just a second. And I will just say that when this topic was first covered, beginning in the 1960s, it was covered by a man named Alan Debus, Debus. You can see him and his name more clearly in the second book, who wrote about people he called the Paracelsians after Paracelsus, who made chemical medicines. And he calls them chemical medicines, not alchemical medicines, to associate them more with chemistry. So there we see that traditional approach to the scientific revolution, trying to emphasize the chemical nature of this rather than recognizing the alchemical aspects of what was going on, because these were really alchemists who were making medicines. And then you can see going into 2007 and then 2015, there's been much more work on what is now referred to as alchemical medicine or medical alchemy. For instance, there's Lauren Cassell, who comes out of the University of Cambridge, has written on medicine and magic, on an English, a 16th century English astrologer, an alchemist who was a physician, but you can see she's taking very seriously his alchemy and his astrology here. This isn't considered pseudoscience. This is considered an important part of the development of alchemy and the development of science. And then you can see in this the book on the far right, a 2015 book called Bridging Traditions, Alchemy, Chemistry, and Paracelsian Practices in the Early Modern Era. So here, they're actually trying to bridge these two terms. They're trying to show connections between alchemy and chemistry. So this is sort of another direction of the historiography, but that people are working in this field for sure. So I've talked about for chemical medicine some of the medieval foundations then that we had looked at several weeks ago, the work of Bacon, Rupasissa, and then Pseudo Lul for making sort of alchemical medicines. And then it's built upon in the early modern period. The idea of chemical medicines is greatly expanded, or I should call them alchemical medicines, is greatly expanded under the work of a man named Paracelsus, who's considered pivotal to this. And then sort of alchemical scholars who follow him, Andreas Libavius, who I'll talk about in a minute, and then Jean Bégin. So Libavius is German, and then Bégin is French. And what they do, particularly what Paracelsus does, is he takes this idea of alchemical medicine and he gives a whole theory to it basically. And what he tries to do is displace Aristotle's ideas, as I talked about a few minutes ago, of the four elements, and instead replace them with three elements, or what are sometimes referred to as three principles of sulfur, mercury, and salt. Now, we've seen sulfur and mercury before. The salt is new, and don't think of it as our common table salt. Salts were for Paracelsus had all sorts of meanings, again, sort of metaphysical, kind of spiritual meanings, just like mercury and sulfur did for alchemy. And I should just say he was German as well. He has this very, very long name, and was just referred to as Paracelsus, building on I should say that's a reference to an ancient Roman physician who wrote a book on medicine called Celsus or Celsus, sometimes referred to as. So he took his name basically. He's taking the name of a Roman physician through the Paracelsus. So anyway, these are some images, I think, what people think of what it might have looked like with Paracelsus at work in his alchemical lab making these alchemical medicines. And so again, here are the three elements of Paracelsus that are sometimes also referred to as the tria prima, so the prime three. So we've talked about, remember, the prima materia, that initial material out of which everything's made. Well, for Paracelsus, everything was made out of these three prime materials, basically the tria prima. You've got sulfur, which was affiliated with, or sort of thought to be connected with the soul, mercury connected with the spirit, and then salt with the body. So there's a lot of religious connotations here as well. So Paracelsus was quite an iconoclast and really tried to go against a lot of the Galenic medicine of the period. You can see again he's rejecting the Aristotelian elements. He rejects the Galenic humors, and he really advocates for a sort of chemical understanding of medicines, or chemical preparation of medicines, and chemical understanding of disease. That disease isn't a humoral imbalance. A disease is sort of, each disease is specific and requires a specific kind of remedy. So other alchemists and physicians and also apothecaries followed Paracelsus's teachings, but also those of John of Rupecissa, of Bacon, and others, and wrote treatises on alchemical medicines, including a German man, Andreas Libavius. He was actually a high school teacher, and he lived in the later 16th century and wrote, among other works, he wrote a book called the Alchemia in 1596, where he actually included recipes and instructions for making a whole series of different kinds of chemical medicines, whereas Bacon and John of Rupecissa and Lull had only sort of included recipes for a pretty limited number of medicines and pretty much only using distillation. What you see with Libavius especially is the beginnings of a widening of the different kinds of chemical medicines that would be available, and also a widening of the different kinds of operations that would be used, and doing more and more complex distillations, and also then using the materials that were left over after a distillation. So not the stuff you would collect, not the distillate, but the stuff that was left over in the original vial. They also would do things with that as well and manipulate that to make medicines. So you have an expansion of the different kinds of medicines and an expansion of the different kinds of procedures and practices that were put into place for chemical medicines. And you also see that in another work by this French Jean Béguin, who wrote this Tirocinium Chemicum in 1610, where he expands these categories of basically of chemical medicines even further, to the point where by this point, by the early 17th century, you have a full formulary of chemical medicines that rivaled that of Galenic pharmacy. And so Galenic pharmacy is actually what my area of research is, and what I've written a book manuscript on. And the last chapter of it actually goes into the medieval and the early modern expansion of these chemical remedies, and then looks at how they basically get added to the Galenic formulary as well. So in Galenic pharmacy, you had a bunch of different kinds of medicines, things like oils, um, ointments, plasters, decoctions, they call them, infusions, syrups. Then in the chemical medicine formulary, there's a whole bunch of then medicines that were formulated using alchemical means. So in Galenic pharmacy, there was very, very, very little use of alchemy. The apothecaries tended to say, "This is too complicated for me. I'm going to leave this to the alchemists who really know what they're doing." I mean, if you think about all that symbolic language and everything, that would have been very difficult for the apothecaries to follow. So they let the alchemists basically make those medicines. And over time, the alchemists, as I said, make more and more and more different kinds of medicines to the point where by the late 17th century, they have a whole, I should say by the mid 17th century, they have a whole formulary of all kinds of different medicines to use that are alchemically prepared. And by the late 17th, early 18th century, it actually fuses with Galenic pharmacy in what's called the chemico-Galenic compromise. And I'll talk more about that in just a second. I just gave you a lot of information and I'm going to go over that more in just a minute, but I wanted to kind of set that out there and let you know where this is where my research kind of comes into it also. So there's this early modern expansion of medicines in the works of Paracelsus, Libavius, Bégin, and I should say others. I'm just pulling out some of the few representative, kind of most important examples. But now I want to turn then to the decline of alchemy. So it might seem like things are going really well for alchemy, so why would there be a decline? But what historians of alchemy and chemistry have found is that in the early beginning in the early 17th century and then throughout, I'm sorry, the early 18th century and throughout the rest of the 18th century, alchemy really starts to get kind of a bad name. It goes into decline and is not considered a serious pursuit anymore and is really overtaken by chemistry. Anyone who had been doing alchemy in the 17th century, by the 18th century, they are called by historians chemists. They're calling oftentimes themselves chemists as well, and they're doing different kinds of work, which we'll see as well. They're not pursuing so much the transmutation anymore. And as we'll see, chemical medicines get sort of absorbed into Galenic pharmacy. And what you see then is a real decline in alchemy. And this happens for three different reasons I'm going to go through relatively quickly. In the first place, there's a lot of accusations of fraud, and there had been really throughout the sort of golden age and then into the period of decline. But it seems to increase during the period of decline where governments and kings and leaders of different countries in Europe had always been uncomfortable with alchemists because they could claim to make gold. And if you want to keep your currency stable, someone who can come and just make a bunch of new currency is going to create a big problem for you. And so they were always wary of alchemists. And then you had alchemists who would promise the moon and say, hey, if you hire me or sign a contract with me and pay me and set me up in a lab, I'll make you anything you want. I can make you tons of gold. I can make you silver. I can make you, jewels. And as we know, they couldn't. If they did make anything, it was going to be counterfeit. And so there often were instances of fraud or of someone who signed a contract and then really couldn't live up to what they said. Whether it was fraudulent or not, they still hadn't done what their contract had stipulated. And so there's a lot of accusations of fraud, and alchemists start to get a very bad reputation. Along with that is the chemico-Galenic compromise I talked about a couple minutes ago, where you have this great expansion in terms of the kinds of medicines that the alchemical texts are giving recipes for and the procedures to use for them, to the point where you really have a whole separate set of chemical medicines that went in conjunction, that sort of went, I should say, parallel to Galenic pharmacy. And then in the late 18th century, I'm sorry, the late 17th century, so the late 1600s into the early 1700s, you see these two traditions fuse. And then pharmacy books start to be called, they start to be published with titles where they say this is chemico-galenic pharmacy. So they basically just add the chemical medicines in with the traditional Galenic medicines. And so what I would argue is the chemical medicine side of alchemy. So the alchemical medicines, or I should say the medical alchemy, gets fused with Galenic pharmacy, and in that way is actually sort of taken out of the alchemical arena and put into the pharmaceutical arena. And I think that is what most alchemists were actually doing, was making medicines. Not maybe I think they were trying to make gold, but I think the way they made their living was by making medicines. And once that gets fused with pharmacy, then that side of alchemy really kind of disappears or gets again subsumed into pharmacy. And that's another reason for the decline. And that's my own theory, and something to sort of explore further as one of the reasons why alchemy declines. And let me just show you this. This is a table from the last chapter of my book where I talk about this, of my book manuscript. And what you can see here is a series of books that were published from the late 1400s through 1706, and the different kinds of chemical medicines that they had. So by 1497, we've got a bunch of different kinds of distilled waters. So they're using distillation, they're distilling roses, violets, poppies, like all these things that had been part of actually the Galenic pharmacopoeia. They're actually taking these things and they're mixing them with water and kind of mashing up, say, rose petals and water, and then distilling that, and then that becomes a medicine. So you've got distilled distilled waters by 1497, by 1525, also distilled waters. Then by 1555, so this is that third book, now we're starting to see oils being distilled. So prior to that, we know that we did have presses. Remember the grape presses to make wine that then were used to make the printing press? They were also pressing olives to make olive oil, pressing almonds to make almond oil, sesame oil, all kinds of oils. Now they're starting to distill these oils. And when you distill an oil, you get a much more refined kind of essential oil. That's where this term comes from. They're distilling out the essence. Then by 1574, they've added salts. So that, remember that Paracelsian salt? They've added salt medicines and extracts, which they did through multiple dissolving things into solvents and then filtering them out repeatedly. Then you see Libavius's work, which was from 1594. Oh, I have to add that into my table. He's added spirits in, so he's distilling fermented things to make spirits, medicinal spirits. Then we see 1607, they add tinctures and essences, and those were other medicines prepared alchemically. Then you see Jean Beguin's work with almost all those medicines, and then two Spanish works that use these medicines as well. And you can see, so that last work from 1706 is called, in Spanish, the translation is Arena for Chemico-Galenic Pharmacy. So there you see the chemico-galenic compromise that I talked about a few minutes ago. And then the final reason for the decline of alchemy, I would say, is due to the mechanical philosophy that we talked about last week. The idea of atomism, the idea of the world as a machine and that works according to very precise mechanical laws that can be described quantitatively with mathematical laws. This is also then what leads to the decline of alchemy and the transition to chemistry. So let's turn to that now, the mechanical philosophy and its role in the chemical revolution. So I just want to do a little bit of review of mechanism and matter theory. So I just talked about sort of what the mechanical philosophy was. And just to review a little bit about matter theory, the way that we've looked at it so far is that for Aristotle, matter was made up of the four elements. Those elements had certain characteristics of taste, smell, texture, um, heaviness, lightness, color, due to their qualities. And so and matter could have substantial qualities, which were qualities that if you took them away, it wouldn't be what it is anymore. It's qualities that are inherent to its own substance, and then it also could have accidental qualities, like the color would be an accidental quality. Like I talked about the color of a dog's fur, even if it's black or brown, it's still going to be a dog. So that would be color would be an accidental quality, and the substantial qualities came from that whole idea of hylomorphism of matter and form, where for Aristotle, then each of the four elements had two qualities of either hot, cold, wet, or dry. It would have two pairs of qualities. I should say it would have two qualities from those two opposing pairs of qualities of hot, cold, wet, and dry, and that would determine its substantial characteristics, basically. And so, in that idea of hylomorphism of matter and form, then the form is what gives the qualities to the matter, whereas the matter is basically an inert substance. And for Aristotle, they couldn't exist separate from each other. So that's just a little bit of a review of Aristotelian matter theory. And the final part of that is that for Aristotle, everything on Earth was made up of some combination of earth, air, fire, water, some proportion of one, two, three, or four of these elements on a kind of continuing scale of infinitesimal differences, so that the same two substances, say that you have, let's see, gold isn't such a good example because that was considered sort of perfect, but say you found some kind of lead ore in the ground, or say iron ore. For an Aristotelian, no two pieces of iron would be exactly the same because they wouldn't have exactly the same proportion of combination of elements within it. It was sort of on this continuing scale. At the same time, I mean, they both could be identified as iron. They had enough, qualities and proportions in common to be iron, but they would be slightly different. And what Principe actually argues very effectively is that this is largely because metals found in the earth are often sort of what not pure. They're impure and they have various ores attached to them. So this sort of fits with what people would have been finding, say, in mines and things like that. So that's sort of Aristotelian matter theory. So again, you've got hot, cold, wet, dry of earth, air, fire, water on the left. That'll probably look familiar from way back in that first lecture. And one other thing I just want to say is in earthly materials, the way those everything you would see on earth then would be some sort of compound of different elements together, and they were called compounds, or they were also called mixeds. And you would not have had just one pure element, throughout Earth. Basically, any terrestrial object would be a mixed, would be a compound. And again, then the celestial sphere, though, was composed only of this perfect ethereal material. Then in the middle, you see the middle sort of diagram is then Paracelsus's three principles or three elements. And then on the right, we see another theory of matter that came out of the 17th century mechanical philosophy. And if you remember from last week, this is Descartes' theory of atomism and the vortices, and this idea that the world is only made up of particles, and these particles interact randomly. And that was considered, well, I should say, as we've seen too, in the ancient period, there were people who proposed ideas of atomism, and that has a real resurgence in the 17th century with the effect of the Copernican revolution and the infinite universe. Now you see a turn toward the mechanical philosophy, and with it, atomism that goes along with this idea of this machine of, randomly interacting particles. There's no God directing their motions. Their motions are due to basically, laws of motion that apply on Earth and in the heavens throughout the entire universe. So this is sort of different theories of matter now that we've looked at over time, and it's the atomistic theory that wins out. And once you see atomism take hold in the 17th century, sort of the transition from the alchemist to the chemist is that most chemists then embraced atomistic theory in some way and approached uh, the experiments that they were doing with the assumption that the materials they were looking at were atoms. And even if they weren't willing to go the full atomistic route, they were still highly influenced by these ideas, so that this idea of atomism allowed them to go further with their experiments and with their explanations. So I want to go through some major figures in this sort of transition from alchemy to chemistry through matter theory and atomism. Nicolas Lemery is the first person I want to talk about. He was a Frenchman, a French chemist, I think we could start to call him at this stage. He lived in that later part of the 17th century, right when the Galenic medicines are getting fused with the chemical medicines, and atomism. This is in the time when Descartes' theories have really taken hold, when Newtonian theory has also taken hold, and it's basically a new universe that people are living in. And in response to this, Lemery writes a really famous book called A Course of Chemistry in French. It was translated into many different languages, and in fact, the author of that Arena for Chemico-Galenic Pharmacy I showed you a few minutes ago, he actually translated that work into Spanish. So he was very much influenced by Lemery, and what Lemery argued was that chemical reactions, or that matter is made up of particles that have different shapes, and that the ways these shapes interact explains basically chemical reactions. And so in his theory, his sort of one of the easiest ways to understand this, and the example that's usually given for Lemery is the acid-base reaction. So alkali is actually an Arabic word for materials that act as what we call in modern parlance bases. If you've ever studied chemistry, you know that there are acids and then there are bases. And when acids and bases react with each other, they form a salt and water. Uh, if you didn't study chemistry, I should say, if you've studied chemistry, that is drilled into your head. If you haven't studied chemistry, don't worry. Just know that acid-base reactions are very, very common in chemistry. And the way that Lemery explained an acid-base reaction here was, he said that acids are very pointy, and their sort of sharp flavor, he said, lent them that's how we knew they were pointy, because of their sharp flavor. Whereas bases had sort of these pores in them, and that when an acid and a base reacted with each other, the pointy parts of the acids fit into the pores of the bases, and that's what led to basically their attraction for each other, and then the kinds of reactions that you would see. This doesn't hold up very long, this particular theory, but what's interesting about it is his attempt at a mechanical explanation for the acid-base reactions. So that's sort of example of this mechanical philosophy in action, basically, in early ideas of chemistry in the later 17th century. And now I'm going to go through 3 steps that really lead to the chemical revolution, and then the kind of the triumph of atomism. So now we are turning to the more traditional interpretation of the chemical revolution, whereas all the material we've looked at concerning alchemy, chrysopoeia, and the chemical medicines, you are not going to find that in a traditional book on the scientific revolution, a traditional history book. So that part of this is sort of innovative or relatively new in the historiography. Now we're going to turn to the more traditional approach, and you'll see the great men. Although we've talked about a lot of men already in this lecture, but we're going to sort of turn to the great men of the chemical revolution, and in particular Robert Boyle and Antoine Laurent Lavoisier. So, like I said, that we're going to talk about this happening in three steps. So we've got this sort of alchemical situation, and we're in the early 1600s. We've got alchemists still pursuing transmutation of metals, still understanding metals as mixtures of mercury and sulfur. We've got Paracelsus making chemical medicines, and then others that are expanding that. And now we're seeing then the impact of the mechanical philosophy on alchemy, really turning it into chemistry with Lemery as that first step. And now let's go to these then three other steps that lead to the chemical revolution. And once we come out of the chemical revolution, we're going to have modern chemical nomenclature in place. We're going to have isolated elements that are recognized in the modern day of hydrogen and oxygen, and actually others. And then the beginning of a search for more and more and more elements that then leads to the putting together of the periodic chart in the 19th century, which goes beyond what we're going to cover here. But you've got a full-fledged theory of atomism in place. And then, as I said, modern names for chemicals as well. The recognition that water is a compound of hydrogen and oxygen. And now the term compound is being used in the way that we use it in modern chemistry, a chemical compound, rather than an Aristotelian mixed or an Aristotelian compound, which would be a compound of earth, air, fire, and water. And then, like I said in the very beginning of the lecture, the recognition that air, earth, and water are not elements themselves, are composed of many different elements, can be separated out, and can be, in the case of water, compounded. That earth is made up of a whole bunch of different kinds of airs, and that in fact everything can be turned into an air if you get a high enough temperature. So there's a lot of changes that take place because of the different steps I'm going to talk about. So the first step then, or actually I should say the first step is the mechanical philosophy and its influence on chemical thinkers. So let me turn to then the second step now is the recognition of the phenomenon of vaporization, or the recognition that basically if you heat something to a high enough temperature, it will vaporize. It will turn into air. And so what we think of as air or atmospheric air, it consists of gases that are, how can I say, that are gases at, say, room temperature, at sort of normal temperatures. But if you take water and you heat it up, water is a liquid at room temperature. If you heat it up, what happens? It turns into steam. It basically vaporizes. It turns into a gas. If you do that with, you can do that with solids. You can heat a solid up. If, say, you take a piece of ice and then you let it melt, then it turns to liquid. Then you heat it, it turns into a vapor. And so a series of sort of chemical experiments take place in the 17th century that start to show these chemists that this is true, that if you heat things and distill them, air is released, or what they started to call fixed air, air that was fixed inside of these substances gets released. And then we'll see the next step is there are different kinds of air. So how does this happen? There is a British scholar who lived in the later 17th century, Stephen Hales, who starts to carry out all kinds of distillations on, basically anything he could find. He basically starts to, distill blood. He distills all kinds of different kinds of organic materials. And what he finds is that when he distills them, as you can see on this in this right-hand diagram, that gas is released, that air is released, and he comes to argue then that different organic materials have within them air that has been fixed within them, that when you distill them, that air gets released. And he called this fixed air. And he's still thinking it's Aristotelian air, but it's a new realization, that this air that's all around outside is also inside of things, and inside of mixed, inside of terrestrial compounded substances. And he writes a book called Vegetable Statics. I love that title, in 1727. And so it's called Vegetable Statics, or an account of some statical experiments on the sap in vegetables, being an essay towards a natural history of vegetation. And so he literally is like distilling tree sap, and wood, and things like that. So that's sort of an important early step, that again, there's fixed air within things that then can be released and can be vaporized. And I'm going through this pretty quickly. There are others who are doing experiments as well and realizing this as well. I'm kind of giving you the sort of an overview of this to not get too bogged down in the details, and you can get those details and specifics in the readings. But like I said, I wanted to give you sort of an overview of what's going on to help really guide you through the readings too. I think all of the descriptions of the different chemical reactions going on in these experiments using the old chemical nomenclature can get really confusing. So that's why I'm kind of boiling things down here. Not, no pun intended. Anyway, let's see. Then the second step in this then is the discovery of different kinds of airs, that Aristotle's air isn't just one thing, but rather is composed of lots of different kinds of gases. And kind of one of the earliest steps in this realization comes with various experiments carried out by a man named John Mayow, who was also English. And I should say, pretty much everyone we're going to be talking about from here on out was either affiliated with the Royal Society. If they're British, they were members of the Fellows of the Royal Society in London, if you remember, where that was this sort of scientific society where they carried out experiments and then presented them in public lectures and public demonstrations, or the Academy of Sciences in Paris. So if they're French, they tend to be affiliated with the Academy of Sciences in France, and to be doing experiments and demonstrations there. So what John Mayow does is he realizes that if he puts, like a glass dome over water, and then puts like a little animal, and on the left hand side you can see a mouse there, into this glass dome, that over a certain period of time the mouse will eventually die. And the same with if you put a candle, you light a candle and then you similarly put it in a glass dome, or in water. He found that that it would go out. And I should say, in this case, it didn't have to be over water either. But if they did this over water, then as the mouse, inside this glass dome would die, what they would find is that water was pulled further up into the glass dome. And the same thing with the candle flame. But the main thing they figure out here is that there's a certain kind of air that that things need in order to be able to live, or in the case of the flame, in order to be able to keep going. And that once that's gone, the flame goes out and the mouse dies. So there's a certain kind of air that's necessary for life, and the same thing they would try this with plants. They would put, say, a plant in a glass dome and see if the plant would survive in these kinds of situations as well. So I know what you're thinking. You know that there's not, once they run out, once the poor mouse runs out of oxygen, it's going to die. The candle flame, the same thing. But you can't try to get away from that kind of thinking, because nobody understood this at this stage. What they're just figuring out now is that there's different kinds of airs, and they're starting to differentiate them. And these poor mice are dying in their experiments to do this. Then you get another British scientist, chemist, who is a fellow of the Royal Society, a very, very wealthy aristocrat named Robert Boyle, who lived in the 17th century. And he's famous for a number of different things. Probably most famous for his Boyle's Law, which I'll talk about in just a second. But he wrote, he was paying attention to all of these other experiments that others were doing, and then he wrote a book called the Skeptical Chemist, or Chemico-Physical Doubts and Paradoxes, teaching the spagyrists principles. So the spagyrist was another name for a chemist. The spagyrical art was the art of basically separation and purification. Um, and he says, teaching the spagyrist principles, commonly called hypostatical, as they are wont to be proposed and defended by the generality of alchemists. So you can see him still using the word alchemy here, but certainly within what we would understand to be modern chemistry. So in his researches, basically Boyle comes up with an air pump that is able to create a vacuum, and then through experiments with this air pump, he realizes that as the volume of a gas decreases, the pressure on it increases. And he also is using barometers, which had been developed during this period as well, to be able to measure atmospheric pressure. And so what he does is, as I said, he applies these instruments to be able to measure what happens when, say, the volume of a gas decreases. So when the space that a gas has is compacted, what he finds is that the atmospheric pressure, the barometric pressure of the gas increases. And then as the gas has more room to expand, the pressure decreases. And he's able to come up with this law, again, through his experiments with the air pump, aimed at understanding the nature of air, basically. And so this is known as Boyle's Law, which is basically that pressure and volume are proportional, are inversely proportional to each other. So the more volume, the less pressure; the less volume, the greater the pressure. So here we have another law. We had Kepler's law, I'm sorry, Galileo's law. No, actually, Kepler comes first. Kepler's law of planetary motion. Then we've seen Galileo's law of acceleration. Then Newton's laws of motion and the laws of gravity, where we're getting, again, quantification and mathematics applied. And so here we have Boyle's law as well, again, showing you the impact of the mechanical philosophy and the importance of measuring nature. So that's Boyle. So here it is again, just another view of Boyle's law. And now we come to the final stage of understandings about the nature of gases that leads to the sort of final stage of the chemical revolution, and that comes from increasing understandings of combustion and how that works. And I'll explain what phlogiston is in just a minute. But first I want to just talk about what combustion is. So combustion is just basically when things burn. And when things burn, they take oxygen from the air and it gets sort of fixed into whatever is burned. That's how we understand it today. And but like I said, there was not this understanding going into the kind of the later 18th century, even though people are recognizing now that everything can be vaporized. They're realizing that there's all different kinds of vapors or airs. Now they're going to start to realize what oxygen is, and from that be able to then move on to identify a whole bunch of other elements, elements in the modern sense of the word. And in particular, a very common combustion procedure that was carried out among alchemists, and I should say apothecaries did this as well, and these are actually absolutely ancient procedures, was calcination, which is basically the combustion of any material that's done very, very slowly in order to turn it into an ash. And so what people did from ancient times was in order to, and I should say the calcinated material would often show alkaline or basic properties and could be used in various kinds of ways. So there were lots of different reasons to do calcination, which I won't go into here, but it was practiced quite often. I can just tell you this from my own research that oftentimes animal horns and claws were calcined. That's the verb, or calcinated is another verb for it, in order to produce alkaline ash, sort of base ash with sort of basic properties to it. So on the left hand side of these images, you can see a combustion of some kind of material, and then on the right you can see sort of a modern version of calcination. But basically, to do it properly, you would do it very, very slowly and heat things at a very even temperature and do it slowly. It's kind of like if you've ever, used charcoal to cook something. You set the charcoal on fire, then you let it burn, and then what's left eventually is the ash. That, and the same thing with wood. If you've ever uh, had a wood, seen a wood burning fire, is same thing, that the ash at the end is the result of the combustion, or what would be called calcination. And so, as I said, there was lots of calcination going on the left hand side is actually bone ash. So bones were also calcined quite often. And then on the right hand side, you see lead oxide. So this is lead that has been calcined and then has basically taken oxygen from the atmospheric air to create a lead oxide. And that's on the right hand side. And the way that calcination was understood tells us a lot about how people understood matter and matter theory in the later, this is sort of moving into the 18th century. In particular, the way that a German scholar named George Ernst Stahl described calcination was, he said that actually when something burns, so when something is, so in the combustion reaction, basically is how we would call it today, there's something inside the material that's burned called phlogiston. And when it's burned, that phlogiston gets released into the air, and then what you have left is the ash of whatever it was you had burned that has no more phlogiston. So the combustion reaction then for him was the release of phlogiston into the air. So let me show you another sort of image of this. So in this case, they're burning metals. So again, for Stahl, what this would have meant was when you burn a metal, when you calcine a metal, and I should say what you would produce with that, the ash that then was produced was called the calx, C-A-L-X. So when you are burning metal, in this case, then you would end up releasing phlogiston into the air. And so, whereas the air previously had been what they called dephlogisticated air, so it had no phlogiston in it, now it's full of phlogiston. And then you produced your calx. But there came a point where, in various experiments that they carried out, that these reactions would only go so far. And so what they started to say was that when the phlogiston reached a certain level in the air, no more of it could be, the air couldn't absorb any more of it, and so these reactions would just stop. And to go back to the mouse in the glass dome experiments and the candle flame, the way they explained that was they said, well, um, because so the mouse is, sitting in this glass dome, and you've got, as the mouse is breathing. No. So the way they explained this, in the glass dome experiments, like for instance with the candle flame, is what they argued was that as the candle flame is burning, it's releasing phlogiston into the air. And in this closed container, once the air got saturated with phlogiston, it couldn't take any more. And so the candle would basically, the flame would burn out. The flame would disappear. And so they explained these reactions in a way that's really kind of opposite to the way we understand them. Whereas we would understand combustion as taking oxygen and fixing it into the metal you're burning, they understood it as the combustion was releasing something out into the air. But what they had a really hard time explaining was the fact that when people started weighing the amount of, say, metal that they were going to burn or whatever they were going to burn, they started weighing it. And then they would weigh it after they burned it, and they found that it actually weighed more. But you would think when you burned it and it released the phlogiston, now it should be lighter. It shouldn't be heavier. So they didn't know how to explain why the calx would be heavier. And so what they started to say was, well, phlogiston actually has negative weight. So when you take it away, when phlogiston is in something, it's actually making it lighter, and when you take it out, it's going to make it heavier. It's a little bit, seems a little bit counterintuitive to us, a little bit hard to get your mind around. But I will say that fire is involved, in calcination, and for Aristotle, fire tended upward. It would rise, and so it was considered to be very, very light. And so there was some rationale for thinking of phlogiston as sort of, as having negative weight, but it was one of those things, like with the Ptolemaic epicycles, nobody was really happy with that explanation, or with the projectiles for Aristotle. Nobody really bought it. No, it wasn't a very satisfactory explanation for it. And so you get a whole series of chemists then who start, or I should say scholars, who start to do experiments on I'm sorry, I keep saying that, on combustion, and trying to figure it out and doing experiments with it. And so I just want to show you, so in the phlogiston theory, when you burn a metal, what you end up with is the calx of the metal plus a release of phlogiston. For Lavoisier, who then, as we'll talk about in a minute, started to do experiments, it didn't happen that way. When Lavoisier started to approach combustion experiments, he, instead of assuming that something already had phlogiston in it, he assumed, what if there's something in the air that's then being fixed into the substance? And this is where the Stephen Hale's vegetable statics then can play a role. You can see the idea of having fixed air within substances. Lavoisier was able to use that idea to try to understand what happens in combustion. So I'm going to go through the Lavoisier theory more in just a minute, but I wanted to show you the phlogiston theory here because it can be hard to understand. So we get another British intellectual member of the Royal Society named Joseph Priestley, who does a bunch of also experiments with combustion and trying to explain things. Here, all of these people I'm talking about our sort of heroes of British and French science. You can here's a statue of Joseph Priestley. He had a lab in sort of a mansion, a country house mansion of an aristocrat. Here's a picture of his lab. And what he did, sort of along the lines of Stephen Hales and Mayau, what he did was similar. He would put basically glass cylinders into water and then put all kinds of different things, plants, animals, metals, and see what would happen. And through these experiments, he was able to actually figure out that there was a kind of air that contributed to life, that, basically that the mice would breathe, that when it was present, things would stay alive and the candle flame would stay lit. And once it was dissipated, then the candle would go out and the mouse would die. And he actually called this dephlogisticated air. Uh, and then, by contrast, also realized that there was another kind of air, basically what we would consider, what we would call carbon dioxide, that was produced, say, in these domes, so where the mouse was, and that this air uh, was very soluble in water, and he actually then was able to put carbon dioxide into water and produce basically seltzer water or soda water, carbonated water. Comes from Joseph Priestley. So the main point of this, though, is that he was able to recognize and identify different kinds of air, and in particular, this dephlogisticated air, which is basically what we think of as oxygen. Um, so he's not getting out of the phlogiston theory, but he is definitely recognizing these different kinds of airs and understanding their properties. And he wrote starting in 1775, he wrote actually a 6-volume treatise on experiments and observations on different kinds of air. So again, you can see this very, very important realization that there isn't just one air. And it's really his work that puts to rest any remaining lingering Aristotelian, four elements. It really gets destroyed once and for all for good with Priestley's work. And then we turn to the person who sort of ties this all together, pulls this all together, and gets away from the phlogiston theory, and that is Antoine Laurent Lavoisier. He was a French aristocrat. You can see him in the two images. Well, I should say in the image on the left, he's clearly a very wealthy member of the elite. He was educated actually not in the sciences, but was always really fascinated by them and ended up spending much of his adult life doing various scientific experiments in a variety of fields, just like all of these people that we've talked about, but really, really interested in air and understanding particularly combustion and the combustion reactions, and why, what was happening during these reactions, and why the calx would be heavier than the material that you started with. And then you can see him in the middle there, and then on the right is a very famous painting with his wife that's painted by a really famous French artist. And his wife was considered to be really his sort of partner in his scientific research. She would take notes during the experiments and actually translated a bunch of his work into English, and was considered to be really, really important in his chemical experimentation. So you can see them there again with all of the sort of chemical apparatus in this painting. And here's a statue of him that's in the City Hall in Paris. Again, another great sort of famous hero of science here, of French science. And here is actually a replica of his laboratory. in Paris today, where he did his work at the Academy of Sciences. He became a member of the Academy of Sciences after actually winning a competition on how to best make street lamps through the city of Paris. That's where he sort of got his fame and then was accepted into the Academy of Sciences. So here's his laboratory, and then here's some images of him doing some experiments, in particular a combustion experiment that allowed him to realize that it wasn't phlogiston. And in fact, as I said earlier, he didn't approach the problem with phlogiston in mind. Instead, he approached it a different way. But here he is doing his experiments that lead him to conclude that this dephlogisticated air is oxygen, or what he's going to name it oxygen, and then get away from the phlogiston theory. So here again is a respiration experiment that he did. And so what Lavoisier's sort of great contribution through his experimentation is that he realized that when you have combustion that happens in, say, in calcination, that it's not that the metal releases phlogiston, or that the heat of the fire makes the phlogiston release, but instead what happens is that the combustion that happens means that that oxygen is pulled out of the atmospheric air and then reacts with the metal to make a metallic oxide. So basically the metal combines with oxygen to make the calx, or again what we would say in modern language as a metal oxide. And that explained why the calx, or the metal oxide, was heavier than the metal that you began with. You didn't have to go to any kind of negative weight argument about phlogiston that wasn't satisfying at all. This was much more satisfying and much more explanatory. And the reason why Lavoisier called this I should not call it dephlogisticated air, but why he called this particular kind of air oxygen was because he also did experiments with it, sort of acid-base experiments. And what he found was that if oxygen was, or this particular kind of air was involved, it would form an acid. And so oxygen actually literally means acid former. He, Subsequent chemists found that it actually isn't the oxygen that makes an acid acidic. It's actually the hydrogen atoms in acid. If you haven't studied chemistry, don't worry about this at all. But I just would say that just know that Lavoisier was actually wrong, that oxygen is the thing that forms the acid and makes the acidic qualities. But the name oxygen stuck, and then very soon after, a man by the name of Cavendish in England is able to isolate hydrogen, and then they actually find that if they were to take that hydrogen and run an electric spark through it, so bring in basically energy and heat, that would basically do the same thing as combustion in terms of pulling oxygen in from the air to combine with hydrogen. And what they found was when they would do that, say they did that in a glass chamber, they would find little droplets of water on the sides of the glass chamber, and they were trying to figure out why. But for Lavoisier, it made perfect sense. He realized that water was formed out of hydrogen, which had previously been called inflammable air, and then the dephlogisticated air, which is now called oxygen. So Lavoisier renames them hydrogen, oxygen, realizes that water is a combination of these two, now he's calling them elements, and so that water is actually a compound of hydrogen and oxygen. And so this then destroys another Aristotelian element. So you've got basically the idea of earth as a pure element. Aristotelian element has been destroyed because you know that if you heat any thing that's solid made out of supposedly earth, for Aristotle, it will turn into a liquid and then it will vaporize at high enough temperatures. So Earth isn't what we thought it was in terms of an element, for Aristotle. Now we know that air is made up of all kinds of different kinds of gases. Now we know there's hydrogen and oxygen, and then we know that water is made out of hydrogen and oxygen. So these three elements of Aristotle's elements, the three of the four, have been completely debunked in terms of being elements. And then fire is left to deal with. That comes with laws of thermodynamics going into the 19th century. So those are going to be beyond the scope here. So they still have to contend with fire and heat and figuring out what they are. They rename it caloric at this stage, but it takes a little while longer to sort of figure that all out. But for now, we are firmly in an atomistic universe. We are firmly on a path toward then, now if we've discovered these two elements, let's try to go about discovering more. And they actually are doing that very quickly at this stage too. And Lavoisier had sort of figured out others as well. So I just want to show you, here was Cavendish's apparatus for collecting hydrogen, or what he called inflammable air. And then we have Lavoisier's apparatus here for the synthesis of water, that he was able to again figure out that hydrogen and oxygen combine to form water. And with that, then he applies this kind of nomenclature, this terminology, not only to hydrogen and oxygen, but he makes a much more systematic way of naming different chemical compounds too. And so he's credited with that too. And the chemical revolution is often referred to as a revolution in naming, as well as this sort of mechanistic revolution as well. So that concludes our lecture on alchemy and the chemical revolution. And next we will turn to Darwin, theories of evolution, early theories of evolution, and then Darwin's theory of evolution through natural selection.